This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to today's discussion. We'll be delving into two fascinating technical papers focusing on open educational resources, OER, in physics, specifically interactive simulations. The first paper details a website packed with these simulations, while the second provides a glimpse into the technical specifications of one such simulation. What immediately strikes you about the concept of OER in physics education?
The potential for widespread access to high-quality learning materials is incredibly exciting. OER levels the playing field, ensuring that students from diverse backgrounds have equal opportunities to engage with engaging and interactive physics content. The use of simulations in particular can make abstract concepts more concrete and easier to grasp.
The first paper mentions easy JavaScript simulations, EJS. What role does this technology play in making these resources accessible and engaging?
EJS is a crucial element. It allows for the creation of interactive simulations that run directly in a web browser, eliminating the need for specialized software or plugins. This makes the resources readily available to anyone with an internet connection, regardless of their device or operating system. The interactive nature of EJS simulations allows students to actively explore physics concepts rather than passively reading about them.
The paper highlights the tracker ball drop simulation. For a student unfamiliar with this, can you explain its purpose and how it works?
The tracker ball drop simulation is designed to help students visualize and understand the principles of motion, particularly the free fall and projectile motion. It uses video analysis to track the movement of a ball, allowing students to collect and analyze data on its position, velocity, and acceleration. This hands-on approach helps solidify their understanding of key kinematic and dynamic concepts.
The simulation is designed for secondary and junior college levels. How does the complexity of the simulation adapt to these different learning stages?
The core concepts remain the same, but the level of detail and the types of analysis offered can be adjusted. For secondary school, the focus might be on basic kinematic concepts like displacement and velocity. At the junior college level, more advanced concepts like air resistance and energy considerations can be introduced.
The paper mentions tracker software. How does this integrate with the simulation, and what are its benefits?
Tracker is a video analysis tool that allows users to precisely track the ball's movement frame by frame. This provides accurate data for analysis, allowing students to test their understanding of theoretical concepts against real-world observations. It bridges the gap between theory and practical application.
Let's shift to limitations. What are some potential drawbacks of using simulations like this to learn physics?
Simulations, while powerful, are still simplified models of reality. They may not account for all the complexities of real-world scenarios, such as air currents or imperfections in the ball's shape. Over-reliance on simulations without hands-on experiments could hinder the development of practical skills and critical thinking.
The first paper also mentions a Creative Commons license. What does this mean for educators and students who want to use these resources?
The Creative Commons license signifies that the resources are freely available for use, adaptation, and sharing, provided proper attribution is given. This fosters collaboration and allows educators to customize the materials to better suit their students' needs.
Now let's move on to the second paper. This one focuses on the technical aspects of a web page, including HTTP headers. What information do these headers provide, and why are they important?
HTTP headers contain crucial metadata about the web page and the server's response. They include information like the date, server type, content encoding, caching instructions, and security settings. Understanding these headers is essential for web developers and network administrators to ensure efficient and secure web communication.
The headers mention gzip encoding. What is the purpose of this, and what are its benefits?
Gzip is a compression algorithm that reduces the size of the web page's content. This speeds up the loading time for users, improving the overall user experience. It also reduces bandwidth consumption, which is particularly important for users with limited internet access.
The headers also include access control allow origin. What does this signify in terms of security and web access?
This header indicates that the web page allows access from any origin, meaning any website or domain can access its resources. While convenient, it also presents a security risk if not implemented carefully. It's generally recommended to restrict access to specific origins to prevent unauthorized access.
The second paper is much shorter than the first. What does this brevity suggest about its purpose and the information it conveys?
The brevity suggests that this paper focuses on a specific technical aspect of the website, namely the server's response headers. It provides essential information for understanding the technical infrastructure behind the website and how it handles requests.
Considering both papers, what are the key takeaways for students interested in physics and the use of technology in education?
The key takeaway is the transformative potential of OER and interactive simulations in making physics education more accessible, engaging, and effective. The combination of readily available resources and powerful technologies like EJS can significantly enhance the learning experience for students of all backgrounds. However, it's crucial to be mindful of the limitations of simulations and to balance them with hands-on experiments and critical thinking. Thank you.